Welcome back everyone. In this lecture, we will classify all finite dimensional irreducible representations of SL2. So, let us begin with some basic observations about SL2 representations. So, let us start with V being a finite dimensional representation of SL2. Suppose V is V actually written as direct sum of H eigenspaces. So, let us call like V A to be the eighth eigenspace. Okay, that means this is those vectors in capital V such that H V acts as A V. Okay. So, it could be 0 or it could be non-zero, but anyway let us assume that this is non-zero inside V, but anyway. So, we are going to just see the action of x on this, so not a problem. So, for A in C, so this is called eighth eigenspace, okay, or weight space. So, if we take this weight space corresponding to the weight A, so A is called weight. So, then we are going to see that how other elements of SL2, basis elements of SL2 acts on this. So, if we take x and then act it on VA, then one can prove that it indeed decreases the value of A by 2. So, this is going to send VA to VA minus 2, and then if we take y and then apply it on VA, so then it is going to send VA to VA plus 2. So, these are the two important observations. So, here for any A, VA denotes the weight space corresponding to the weight A. So, this is the definition of VA. Now, let us check this. Let us start with the vector V in VA. Okay. If it is 0, then there is nothing to prove. Otherwise, what will happen? We want to calculate what will happen to XV. Okay. But what we know, there is this relationship between H and X. The bracket Hx is given by Hx minus Xh, okay, which is exactly equal to given by 2x. Okay. Now, if you take these elements and then apply it on V, then what we get? We get exactly H x V equal to x H V minus 2 x V. But note that H V is nothing but A V. So, x H V is going to be x A V, which is going to be A x V. So, that tells you that this is going to be A x V minus 2 x V. So, that tells you that you can take x V out. So, this is going to be A minus 2 times x V. So, H of x V is given by A minus 2 x V. So, that means the weight of x V, if it is non-zero, is going to be equal to A minus 2. So, then it is clear from this calculation that x applied on V A is going to be subspace of A V A minus 2. And similarly, if we take V in V A and apply Y V, and what will be the H eigenvalue of that? So, we are not only saying that it is mapped to something, it is also H eigenvector, okay, if it is not 0. So, H of Y V is going to be again similarly H y is equal to H y minus Y V equal to minus 2 y. So, this is this is H. So, this is Y H V minus 2 Y V. Similar calculation says that this is going to be A. So, H V is A V, this is going to be minus . So, H x yeah. So, we are calculating HXV sorry, oh, it should be the other way. So, when you apply X, it should increase, when you apply Y, it should decrease actually. So, because Hx is xh plus 2x, so this is going to be plus 2 and this is going to be plus, so this is going to be plus. And when you apply Y, this is going to be minus, because Hy is YH minus 2y. So, this is going to be AV, AYV minus 2YV. So, that is going to give us A minus 2YV, HYV. Okay. So, basically H eigenvalue is A, then X actually increases that A to A plus 2 and then Y actually decreases that to A minus 2. Okay. So, now from this one can immediately conclude that if we take any non-zero SL2 module, then that must contain some highest weight vector. Okay. So, as a corollary, we can see that if V is non-zero SL2 module, of course finite dimensional, then V contains a non-zero, of course by definition it is non-zero, highest weight vector, highest weight vector. So, recall what is highest weight vector, okay. Something called highest weight vector. So, let us call it U, which is inside capital V, and it is highest weight vector with highest weight, let us say A in C. So, then HU should be AU and then XU should be 0. Okay. So, that is why it is called highest weight vector, because the weight is not increased by the action of SL2. So, what is the proof? The proof is you start with V being actually non-zero SL2 module. So, that means H will have some eigenvector, will have eigenvector inside capital V, because H is being operator and we are working over complex numbers, any operator will have eigenvalue. So, there will be corresponding eigenvector. Take that eigenvector to be V, which is inside capital V. Let us say the eigenvalue is B. Okay. This is the weight of this V. So, weight of V is B. So, B could be 0 and all, we do not need to worry about it. So, now what happens if you apply X? If you apply X on V, so this is going to lie inside V B plus 2, because the action of X actually increases the weight by 2. So, that means if you apply X on V, that is going to give you V B plus 2. Now, you keep applying, okay, keep applying X. So, then what will happen? So, we will be getting x power I V, which is going to lie inside B plus 2I. Note that B plus 2I all are distinct values inside C. So, if xi V, if it is actually non-zero for all I, then that will give you distinct eigen vectors for the distinct eigenvalues B plus 2I. So, then using that you can produce infinitely many linearly independent vectors inside capital V. So, that is not going to happen, because V is assumed to be finite dimensional. So, that implies that there exists I inside Z plus such that x power I V is 0. Now, you take U to be x power I V, then it is clear that H U is nothing but B plus 2y U, and then x power x times U is nothing but 0. Okay. You take I minus 1, here you get I minus 1. So, you take u to be x power I minus 1 v, because x power I v is 0. So, then x u becomes 0, and since u is eigenvector for h, so it has the corresponding eigenvalue. So, a you take it to be b plus 2 I minus 1. So, that means we have highest weight vector inside capital V. So, now what we can do with this highest weight vector? Okay, you start with V, which is a finite dimensional representation of SL2. So, let us say V, which is non-zero highest weight vector inside, highest weight vector with weight, let us say capital A, sorry, small a. So, as of now we know that this weight can be only complex number. Okay. Now, using this weight, let us see what one can do. So, let us just relabel, maybe we can actually call this W naught. Okay. So, W naught is the highest weight vector with the weight A. So, now we know that H W naught is equal to A W naught and X W naught is equal to 0. So, as before we have this W naught that is coming from our earlier lecture. Okay. Now, you see what one can do using W naught. Now, we can actually apply y on W naught and then consider various powers of y applied on W naught and then see what one can get it from that. So, let us take this decorated vector, call it Wi. So, this coefficients, not coefficient, the scalars are adjust so that the formulas works very well. Okay. So, let this Wi to be the following vector. You take 1 divided by I factorial times y power I W naught. Okay. So, basically what we are interested in? We are interested in understanding SL2 submodule generated by W naught. So, SL2 submodule generated by W naught. So, that is what we are interested in. So, indeed we are going to prove the SL2 submodule generated by W naught can be obtained from W naught by applying various powers of y. So, we do not need to really worry about the H action or W action, sorry X action. So, the H action is going to give you scalar on W naught, X is going to kill. But instead of taking various powers of H, X and Y, so that is the way to get a submodule generated by W naught. So, we are going to say that it is enough to take only the powers of Y and then we can still get a submodule of generated by W naught. So, this is something we have seen already. So, this is simple exercise which says that this is going to be span of some complex number where you can take some like all possible powers, okay, like x power some m1, h power m2 and then okay, let us call it sigma of this m3, where this m1, m2 and m3 these are all various powers. So, exponents running over z plus, and this sigma is just a permutation of these 3 letters x, h and y. So, if you take all possible permutation and all possible powers and then you apply it on W naught, then you will be getting this entire span of this SL2 submodule generated by W naught. But now, what we are going to claim, this is the powerful claim indeed, this SL2 module generated by W naught is going to be just span of these Wi's. Okay. So, then later we will see that there we can choose some power such a way that something will be actually killed. Okay. Okay. So, let's try to prove this one by one. So, we will actually once we set this Wi, which is 1 divided by I factorial times y power I W naught. So, then one can see that this SL2 module generated by W naught, this has this very explicit basis. Okay. So, indeed one can prove much more stronger statement. The basis of this, so this is span by, so this is the basis W naught, W 1, etc., W m. Okay. And these W i's, they are basis of this SL2 module, submodule generated by W naught inside this capital V. Okay. So, this is the action of SL2 on these vectors are given as follows. So, when you take H acting on Wi, you are going to get m minus 2I Wi. So, this is exactly the formula that we have seen already. Okay. So, this is the formula that you see it in SM. So, x Wi is going to be m minus I plus 1 Wi minus 1, where we said that W minus 1 is 0 and then I varies from 0 to m. Okay. And y Wi is going to be I plus 1 Wi plus 1, again we said that W m plus 1 is 0 and again I runs over 0 to m. Okay. So, to prove that it is indeed SL2 submodule, we need to actually check. So, obviously, like if you take the SL2 submodule generated by W naught, so that is going to contain all this W naught etc. W m, because they are all powers of y power applied on W naught. Okay. So, the one side is obvious. So, to prove the other side, what we will prove, we will take this span of this. Okay. Then we directly prove that it is going to be SL2 submodule. Then that is going to say that because this is SL2 submodule containing W naught, so this must contain the submodule generated by W naught. So, then that will force that these two modules are same. Okay. Let us call this is W 1 and this is W 2. Now, it is clear that W 1 contains W 2. Okay, W 1 contains W 2, this is easy. Why? Because W naught in W 2, and if you take y power W naught, that is going to lie inside W 1, that forces W 2 is contained in W 1. Okay. So, now we to prove the other side, to prove W 2 contains W 1, it is enough to prove that W 2 is indeed SL2 module, SL2 submodule. So, once you prove it is SL2 submodule, then the W naught is being inside W 2 will imply the submodule generated by W 2, which is W 1 is subset of W 2. So, that will imply that W 2 is equal to W 1. So, this is the strategy. To prove this is indeed SL2 submodule, we need to check that these formulas indeed gives you SL2 action. So, that I will leave it as exercise, because this is routine exercise. Okay. Whenever you take H x minus x h applied on W I, then you should get 2 x W I. This is the one thing that you need to check. Similarly, there are other two formulas that also one can check. So, check that. Okay, check that W 2 is SL2 submodule. Okay, this is plain computation, so we do not want to check. Now, we will verify these formulas. Okay, once we verify these formulas, then these formulas also actually immediately tells that. So, yeah, we do not need to check these things because it is already part of capital V. So, these formulas immediately tells you that W2 is indeed submodule. So, we do not need to check anything. So, only thing we need to check is we need to check that these formulas are true. So, let us check that. Okay, maybe I will check only the first formulas. Okay. So, it is easy to see that if you apply y on Wi, so this is going to be y 1 divided by I factorial applied on y power I W naught. So, this is going to give me exactly 1 divided by I factorial y power I plus 1 W naught. So, then this is you multiply I plus 1 and then divided by I plus 1. So, then it gives me exactly I plus 1 times Wi plus 1. So, the third formula is easy to verify. Okay. So, this is done. So, now let us verify the first formula HWI should be m minus 2IWI. Again that can be verified directly using the commutation relations. Okay. So, for example, if we know already that if y v is if h v is a v, then y h acting on y v is going to be a minus 2. Okay, let us check the formula. So, here, so h y v is a minus 2 y v. So, if you use that formula, so we get h y v equal to a minus 2 y v. So, now by induction you can see that h y power I v, okay, 1 divided by I factorial. So, that is what we want to compute. So, this is going to be h 1 by I, okay. So, let me take it out 1 by I h y acting on W I minus 1. This is going to give me, so by induction you can assume that y I w, by induction you can assume that h W I minus 1 is going to be exactly m minus twice I minus 1 W I minus 1. So, using that you can see that. So, this is going to give us 1 by I h, this is the formula that I am using. So, this is going to be use this formula. So, m minus twice I minus 1 minus 2 and then y times W I minus 1. So, y times W I minus 1 is going to be again I times W I. Okay. So, this is going to be I times W I. So, then we get h W I equal to m minus 2 I plus 2 minus 2. So, this get cancelled. So, here 1 divided by I is there. So, this I get cancelled and gives you W I. So, h W I is exactly m minus 2 I W I. Okay, this is also verified. So, now I will leave it to you to check that the third formula x W I is nothing but m minus I plus 1 times y W I minus 1. Okay. So, basically these formulas are true and these formulas immediately tells that because V is SL2 submodule, SL2 module. So, the span of W0 etc. Wm is also SL2 submodule, and that forces that W1 has to be equal to W2. So, in particularly all the eigen values of H eigen values of these vectors, they are all distinct. So, this will be linearly independent. So, that will form a basis for this SL2 module generated by W0. So, now what is the immediate corollary of this result? If you start with irreducible representation, okay, so immediate corollary, if V is finite dimensional irreducible SL2 representation, then by using the early result there exists highest weight vector of highest weight m. Okay. So, sorry, we have used this highest weight as A. So, maybe I should actually tell you that what is the connection between A and M. Okay, I will stop. Thank you. I will stop here.